Welcome to another deep dive. Today, we're plunging into a really fascinating set of sources.
Yeah, these ones unpack one of the most, well, profound paradoxes of the cosmos.
Exactly. The incredible interplay of time, space, and perception. Get ready to maybe rethink what now truly means.
We're going to explore that mind-bending reality of distant observations,
Right.
what it truly means to exist for someone light years away.
And whether interstellar travel is still just sci-fi or maybe a future reality.
And of course, what all this implies for that huge question, are we alone out there?
Okay, so our mission today is to sift through your notes, the sources on the paradox of time and space, and pull out the key insights.
Yeah, the nuggets of knowledge.
This isn't just about, understanding the universe in an abstract way.
No, it's really about understanding our place within it, this dynamic, always unfolding story.
So we'll be looking at how light itself is kind of a cosmic time machine.
Exactly. How that affects what we see, what distant observers might see of it, and why our physics might need a revolutionary shift for real interstellar journeys. Let's get into it.
Okay, so we kind of get that light takes time.
Hmm.
We look at a star, we see its past. Simple enough, right?
Well, yes, but the sources dig deeper.
Because if we see their past,
Do they see ours? And what does that actually mean for something as basic as now?
right, the present moment.
Precisely. The further the distance, the older the information the light carries. It's fundamental.
So studying distant galaxies,
Yeah.
it's literally looking back in time
Now-
into cosmic history.
And the key thing the sources stress is this applies universally. It works both ways.
Okay, so that leads to a wild thought. How far away would some alien observer need to be to see Earth now, but as it was, say, during the Middle Ages?
Right. Okay. So for an observer to see Earth around, let's say, 1000 AD, height of the Middle Ages,
Yeah.
they'd have to be roughly 125 light years away from us.
Wow. 125 light years.
Yeah, the light carrying images of, castles, Viking ships, early kingdoms, they would only just be arriving there today.
That's almost surreal to think about. While we're having this conversation, someone, somewhere could be watching, I don't know, ancient Egyptians building pyramids
Or Romans or dinosaurs, depending on the distance.
Yeah.
They wouldn't see our cities, our tech, us. Not right now.
So
Yeah.
what does exist simultaneously
Mm-hmm.
if their now and our now are showing different times?
That's a crucial question the sources tackle. While synchronized views are impossible,
Right.
the physical objects, stars, planets, galaxies, they do exist. We just see them at different points in their history.
Okay.
And the fundamental laws of physics, gravity, electromagnetism, thermodynamics, space-time itself, those are universal. They exist for everyone, everywhere, simultaneously in that sense.
So the present is really, truly local. It's tied to your specific spot in space-time.
Exactly. That's a core idea from Einstein's special relativity. Your now is yours, theirs is theirs.
Okay, but here's the paradox kicking in again. If that civilization, 1025 light years away, is watching our Middle Ages, and then they decide, okay, let's go visit. They hop in their super advanced ships.
Right.
They wouldn't find knights and castles when they arrived, would they?
Absolutely not. No chance. They would arrive here, well, in our present.
Or even our future, depending on how long their trip took.
Precisely. They'd find, modern cities, cars, the internet, maybe things we haven't even invented yet if the journey takes centuries from their perspective.
So traveling through space is traveling through time, just forward into the destination's future relative to the light you first saw.
Yes. And the sources use a great analogy for this.
Ah, the football match one.
Yeah. Imagine watching a recording of a match from last week.
Yeah.
You're seeing the past, right?
Okay, got it.
If you then drive to the stadium today, you won't find that game. You'll find maybe training or a totally different match.
Right. The stadium's local present.
Exactly. Looking through a telescope is like watching that recording. Traveling by ship is like driving to the stadium. You arrive in the local present of wherever you're going.
Which brings us to the huge challenge, the time it takes, the speed limit.
The universal speed limit. Our sources really hammer this home. Einstein's special relativity. Nothing with mass can reach, let alone exceed, the speed of light in a vacuum. Period.
And just to underline how limiting that is, you mentioned the Parker Solar Probe.
Yes, our fastest spacecraft.
It travels at what, like 0.064% of light speed? Tiny fraction.
That's right. And even at that speed, getting to Proxima Centauri, our nearest star neighbor,
Only 4.2 light years away.
will take about 6,600 years.
6,600 years. Just Staggering. Way beyond a human lifetime. It makes conventional interstellar travel seem almost impossible.
It is the critical limitation, because as you approach light speed, weird things happen.
Relativity kicks in hard.
Your mass increases infinitely, time slows down for you, that's time dilation, and you'd need literally infinite energy to actually hit light speed.
Yeah.
So, yeah, it's not just about better rockets, it's fundamental physics.
So if we want to achieve interstellar travel in, say, a human lifetime, we can't just go faster through space in the normal way. We need, well, a shortcut, a loophole.
Exactly what the sources suggest scientists are thinking about. Hypothetical mechanisms. Things that let you travel faster than light effectively, but without actually breaking Einstein's speed limit for objects moving within space-time.
Ah, so you manipulate space-time itself.
That's the idea behind some of these concepts, the shortcuts you mentioned.
Okay, now this is where it gets really sci-fi, but grounded in theory. Let's talk about the big two. Warp drive.
Right, warp drive. So the idea isn't the ship flying through space super fast.
No.
Instead, the drive would distort space-time around the ship. It would kind of scrunch up space in front.
Contracted.
Yeah, contract it, and expand space behind it, creating this bubble that carries the ship along.
And that doesn't break the rules.
Technically, no, because the light speed limit applies to movement through space. The expansion or contraction of space itself, like in the early universe, can happen faster.
But there's a catch.
A huge catch? It seems to require enormous amounts of something called exotic matter.
Exotic matter. Sounds suspicious.
It is. It's theoretical stuff with negative energy or negative mass, things that would, like, repel gravity. We don't know if it exists, let alone how to make or handle it.
Okay, so warp drive needs magic space stuff we don't have. What about the other one? Wormholes.
Wormholes, also theoretical, but predicted as possibilities by general relativity. Think of them as tunnels.
Tunnels through space-time.
Exactly. Like, imagine space-time as a sheet of paper. You want to get from one point to a distant one.
Okay.
Instead of traveling across the paper, you fold the paper over.
Bringing the points close together.
And punch a hole, the wormhole connecting them. A shortcut.
Sounds convenient. Catch?
Same problem, really. To keep a wormhole stable and open long enough for something to pass through you'd likely need.
Let me guess. Exotic matter.
You got it. Or some other physics we don't understand yet. So, fascinating concepts, but purely theoretical for now.
And just to be clear, even if we had warp drives or wormholes, they're about cutting down the travel time, right? Making the trip feasible.
Precisely.
They don't change the fact that when you arrive in that destination's local present. You're not traveling back to see their past history live.
Exactly right. They solve the practical travel time problem, not the observational time delay paradox. You're shortening the journey, not rewinding time at the destination.
Okay. So beyond those really out there ideas, what are scientists actually working on now for propulsion? Stuff that's maybe less FTL, but still better than chemical rockets.
Oh, there's a lot of research. Advanced concepts, definitely. Things like nuclear rockets using fission or even fusion.
More power than chemical.
Way more. Ion propulsion, which is very efficient, just low thrust. We use it already for probes, but scaling it up.
Solar sails, using light pressure.
Yep. Solar sails using the pressure from sunlight or powerful lasers from Earth, like the breakthrough Starshot idea, aiming tiny probes at Proxima Centauri using lasers.
Right, light sails.
So all these aim for much higher speeds or efficiency than we have now, still sublight, but potentially cutting those huge travel times down significantly. Still long, but maybe not impossibly long for probes or perhaps future generations.
Okay, so with all these immense challenges, it really makes you think about other civilizations, doesn't it?
It absolutely does.
Our sources touch on this idea, maybe an assumption, that any truly advanced civilization out there might already have figured some of this out. Technologies we're just dreaming of.
It's a logical thought, isn't it? I mean, the universe is old, like 13.8 billion years old.
And Earth is only about 4.5 billion, relatively young.
So there's been a lot of time for life and intelligence and civilizations to arise elsewhere, potentially billions of years before us.
And if the laws of physics are the same everywhere?
Which we assume they are. Then they would have encountered the same speed limit, the same relativistic effects.
And maybe they found ways around them. Or maybe they just had the time to make those long journeys.
Could be either or both. Maybe they mastered warp tech. Maybe they used generation shifts. Maybe something we can't even conceive of.
Which leads directly to, well, if they could be out there and potentially so advanced, where are they?
Ah, yes. The big one. The Fermi paradox.
Explain that for us again.
It's basically this contradiction. On one side, you have the sheer numbers. Billions of stars in our galaxy, billions of galaxies, likely trillions upon trillions of planets.
Statistically, life should be common, even intelligent life.
The probability seems incredibly high based on what we know. But then the other side is, well, where's the evidence?
No alien megastructures, no obvious signals, no visitors. Where is everybody?
Yeah, exactly. That's the paradox. High probability, zero observation.
So what are the leading ideas, the hypotheses to explain this silence?
The sources list quite a few. Maybe they are too far away, and interstellar travel, even for them, is just too hard or too slow.
Or maybe we just haven't looked hard enough or in the right way. SETI listens for radio. Maybe they use something totally different.
That's a big one. Or maybe communication is dangerous. Maybe they're hiding.
And then there's the darker idea, the great filter.
Right. The idea that there's some step in the development of life or civilization that's incredibly difficult to get past.
Like maybe intelligence inevitably leads to self-destruction, nuclear war, climate change.
Or maybe it's a biogenesis, the start of life itself. That's super rare. Or the jump to complex cells. We don't know if the filter is behind us or still ahead of us.
Chilling thought. Or maybe they're just fundamentally uninterested in contacting species like us.
That's possible too. The zoo hypothesis or similar ideas.
So importantly, these hypotheses aren't saying they don't exist.
Not necessarily, no. Most are trying to explain the lack of evidence or contact, given the high probability they should exist.
There are ways to bridge that gap between the numbers and the silence.
Exactly. And they help us think about how we should search, what challenges might exist, and even, our own future trajectory as a species.
What's the general feeling among scientists these days? Still think we're likely not alone.
I'd say the consensus among many, maybe most, astrophysicists and astrobiologists is still leaning towards not alone. The numbers are just too vast. It feels more like a question of when and how we'll find evidence, not if.
Okay, this whole discussion, from seeing the past in distant stars to maybe warp drives,
Yeah.
it does make you reconsider our current understanding of physics itself.
Absolutely.
Like the theory of relativity, it underpins so much of this. Is it possible that one day, maybe it gets, well, not proven wrong, but superseded, that we do find a way to genuinely go faster than light?
That's a fantastic question. And the history of science is full of theories being refined and expanded, so optimism is good. But it's really important to understand just how solid relativity is, why it's such a pillar.
Okay, why is it considered so robust? More than just a good guess.
Well, it's not just a hypothesis anymore. It's been tested and confirmed relentlessly for over a century. In countless ways.
Like what? Give us some examples.
Okay, well, GPS. The satellites orbiting Earth experience time differently due to their speed and gravity field. Your phone's GPS wouldn't work accurately without applying relativistic corrections.
Wow, okay. Everyday example.
Particle accelerators, like at CERN. They accelerate particles close to light speed, and those particles behave exactly as special relativity predicts. Their mass increases, time dilates for them. And then general relativity predicts things like gravitational lensing, black holes, gravitational waves, all of which we've now observed and confirmed. The expansion of the universe fits within it.
So it describes reality extremely well, on many scales.
Incredibly well. And the speed of light isn't just some random speed limit. In relativity, it's woven into the very fabric of space-time. It defines causality, the order of cause and effect. Breaking it would seem to break fundamental logic in our current understanding.
So if something genuinely faster than light was discovered, it wouldn't just be a tweak, it would be revolutionary.
Completely revolutionary. It likely wouldn't disprove Einstein entirely, just like Einstein didn't disprove Newton.
Right, Newton's laws still work perfectly well for everyday stuff, like throwing a ball.
Exactly. Newton became a special case within Einstein's broader theory. A future FTL theory would probably have to show how relativity emerges as a special case under normal conditions, while also explaining the new FTL phenomena.
And scientists are looking for that next step, right? Trying to unite relativity with quantum mechanics.
Absolutely. That's one of the biggest goals in fundamental physics, finding a theory of everything, or at least a consistent theory of quantum gravity. And who knows, maybe that theory will reveal new principles, loopholes, ways space-time behaves that we currently don't grasp.
So the search goes on. We need that solid, undeniable evidence before we can really overturn such a well-established pillar.
Precisely. Science needs proof. But the mysteries are still out there. Dark matter, dark energy, these show we're missing huge parts of the picture.
Right, like 95% of the universe's energy density.
Yeah. So there's plenty we don't know. And exploring ideas like warp drives and wormholes, even theoretically, is part of pushing those boundaries, seeing if we can manipulate space-time within the known laws, or maybe find where those laws might break down.
Wow, okay. What an incredible journey through these ideas. We started just by thinking about starlight.
Yeah, and realizing that for anyone far away, our present is just an echo drifting through space, a ghost of our past.
And we ended up talking about manipulating space-time, the Fermi paradox, and the very foundations of physics. It's mind-bending stuff.
It really is. The sources show us that now isn't universal, it's local. What we see across space is always delayed.
And interstellar travel. It's this immense hurdle because of fundamental physics, but maybe not impossible if you can somehow bend the rules or find new ones.
Exactly. Those theoretical pathways, warp drives, wormholes, they're long shots based on current knowledge, sure. But they show we're thinking about how the universe might hold surprises.
And maybe the most inspiring part is just the ongoing quest, trying to figure out if we were alone.
Even with the Fermi paradox, that silence, the sheer statistical likelihood, the vastness, it really pushes us to keep looking.
It feels like a when, not an if, somehow.
Many scientists feel that way, and the critical thinking involved in tackling these questions, pushing our understanding, that's how science moves forward, that curiosity.
So thinking about all this, how does it change your perception? Your sense of time, distance, our tiny place in this huge cosmos?
Yeah.
Does it make you feel more connected, seeing that shared, delayed reality? Or maybe more isolated in our own little now?
It's definitely humbling. It underscores the vastness, the strangeness, but also the potential. Keep thinking big.
Keep thinking big, because the universe is definitely bigger and probably much stranger than we can currently imagine.
That's for sure.
Join us next time for another deep dive where we'll unpack more fascinating sources and hopefully uncover some more surprising facts. Until then, keep looking up.